Good evening. As I think most people know, the gallant little space probe Giotto, which went through Halley's Comet way back in 1986, has now had an encounter with a second comet, Grigg Sjkellerup, a very much smaller and less active comet. Unfortunately, the Giotto camera was no longer working, so there aren't any direct pictures. This view of the comet was taken on July the 10th from the European Southern Observatory, but everything else worked very well indeed. Now, comets are the most erratic members of the solar system. They're not solid and rocky like planets, and in fact, even a major comet has a fairly small nucleus, which has been described as a dirty ice ball, not a bad name for it. Only when the comet nears the sun and the ices are warmed do they start to evaporate, and the comet then produces a head or coma, and very often a tail or tails. Now, I don't pretend to be a comet expert, so let me welcome back somebody who is, Dr. John Mason. John, welcome back to the Sky at Night. First of all, what do you think of this latest encounter?
Well, it was a remarkable success, both for the European Space Agency and for all the scientists involved. This, of course, is Giotto's second cometary encounter. It first, as we all remember, flew past Comet Halley in March 1986. And you can see here its orbit relative to the Earth. It's the blue orbit there. It flew past Halley on the 14th of March 86. It then made a flyby of the Earth in July 1990. Its orbit was tweaked slightly, so it went outside the Earth, and you can see that it then rendezvoused with Grigg Sjkellerup, the yellow curve, on the 10th of July. And of course, Halley and Grigg Sjkellerup are very different comets. Halley is a young, bright, active comet producing lots of material. Grigg Sjkellerup is a rather elderly comet with a very low activity. And of course, the nuclei are very different. Halley is rather large, about 16 kilometres long by about 8 kilometres wide on the right here. That of Grigg Sjkellerup is very small, about half to 1 kilometre. And of course, the flyby velocities were much less in the case of Grigg Sjkellerup, 14 kilometres per second as against 68 kilometres per second.
One of the world's leading comet experts is Professor Susan McKenna-Lawler, and we're delighted she's been able to join us now. Now, Susan, you've had experiments on Giotto, both with the Halley pass and with this latest pass, but they're very different, aren't they?
They are very different. The main difference is in the gas and dust production rate. You get 30 tons per second from Halley, and in the case of Grigg Sjkellerup, less than 1% of that. So we could say that in 1 second from Halley, we would have enough material to fill a large truck, and from Grigg Sjkellerup, enough just to pack a small family car.
Well, you've had a very important experiment on board the probe. What exactly does it do?
It measures energetic particles in a particular energy range from 30,000 electron volts to a few million electron volts. And it has 3 telescopes. 2 of them are looking in the forward direction as the spacecraft flies along. One of them gives information on positive particles and the other one on negative particles. The other telescope looks in the backward direction, and the idea is that when we fly through the comet, we still have a telescope that is looking cometwards.
I think it might help here if we had a look at a diagram of the makeup of a comet.
Yes, what you can see there is in front the blue bow shock, and then there's a cutaway section so you can look inside. And in the case of our energetic particles experiment, we would notice a signature there for particles that are energized as they cross the bow shock. And then inside you cross a chemical transition region where the solar wind is shocked and slowed down and becomes stagnant, and the predominant species are from the comet. And you can notice there the pileup of magnetic field around a diamagnetic cavity, which is a teardrop-shaped thing shown there in red.
Let's do some comparisons. First of all, what did you see during the Halley pass?
Let me show you. Here is a plot that we have, which was taken with the number of counts we registered in one of our telescopes against time, which is running this way. Now, out here about 30 hours in front of the comet, you can see a peak, and this is due to pickup ions. These are from neutral particles that come out of the comet. They become ionized and energized in the solar wind, so if they're water group ions, they can attain an energy of about 50,000 electron volts if the solar wind is fairly reasonable, about 400 kilometers per second. So we can see them, and this was the peak that we got. And as you come along here, you can see fluxes building up, and then a very dramatic and sudden rise here where the spacecraft goes over the bow shock. And as I mentioned, this is where energization can take place. Then on the other side, where the solar wind is being shocked and slowed down, the number of energetic particles drops off. Now, when you get here into the stagnation region, we didn't expect to see anything at all. But this is one of the surprises of space flight, that here, if we take up the story, these are panels looking in 4 different directions. Our instrument can record in different directions by making observations every half second. Here, you have the region where we're crossing over the magnetic pile-up region, and you get a great peak building up and falling down again on the other side. And in fact, we got so many particle counts that just here, our counters actually saturated and rolled over, so there was a little drop out there, but we can tell what the peak would have been. And then on the other side, as we flew on the outbound leg of the pass, we had all these very fast fluctuations which have information about the magnetic field draping around the comet.
Well, that was Halley. Now, what did you get this time with Grigg Sjkellerup?
This time, let's compare. Here we have the data that we got as we were flying in towards the comet. Now, here are the 4 directions. The different channels are shown in colors. Let us take this panel here. Red is the lowest energy. It would be about 50,000 electron volts. This one about 100, this one about 150. And you can see that there's no great peak here from the pickup ions. It's all going along fairly steadily, and probably just a very few pickup ions superimposed on solar wind protons. Here there's a very interesting thing is happening where the fluxes drop down, and then if we go this way, we are coming in towards closest approach. And let's switch to this plot here. This plot shows counts against distance from the nucleus, and at this point, when we reach about 17,000 kilometers out from the nucleus, we begin to get a peak. And this is where we went over the bow shock of this comet, we believe.
Did everything go smoothly?
Not very smoothly, I'm afraid, for us, because when we got to closest approach, which is just about here, the spacecraft was struck by a dust particle. It lost the telemetry lock, and everything on my screens went completely blank.
That must have been a nasty moment.
It was one of the nastiest moments I can remember. But one of our other data recording units, our old ground support equipment, was still working through this, and I could see that, so we pressed the restart button, and immediately we began to get the data coming out here. This is the outbound pass. So you can see that again we have these fluctuations and then some sort of boundary here, which is the bow shock being crossed outbound. And if you look here into this, you can see that our 3 traces at this panel are very disturbed, indicating some kind of particle acceleration at the bow shock. But what is very interesting here is that we didn't get the drop down in particles that you saw on the other graphic, and we feel from just looking in a very preliminary way at these data that we went through the tail very close to the nucleus on the other side, just where the tail is beginning to form. So this is something that is new.
It really was a great success then.
Oh, I think so, yes. We learned a lot. We know that there are lots of energetic particles out there, and also because we have flown so close to the nucleus on the tailward side, we have absolutely unique data.
Congratulations, Susan.
Thank you.
Grigg Sjkellerup is a fairly typical short-period comet. It was discovered in 1902, recovered in 1922, but it may have been seen well before that, possibly as long ago as 1808 by Pons.
Yes, it's been seen 13 times since it was recovered by Sjkellerup in 1922, so its orbit, which you can see here, is very well known. It's one of a class of short-period comets, that is, those with periods of less than 200 years, and of the 120 short-period comets that we know, the majority have periods of 30 years or less.
But they've all got their points of interest.
Yes, indeed. Because short-period comets go round the sun so frequently, and every time a comet goes round, a little mass is lost, the ageing processes are accelerated in short-period comets. The lifetime of a typical short-period comet might be anything from a few thousand to 100,000 years, which is very short on the cosmic scale.
And, of course, their mass is very low indeed, so they're always liable to be pulled around by planets.
Yes, you'd need 50,000 million comets of the mass of Comet Halley, which is a reasonable-sized comet, to make up a body the same mass of the Earth. And as you say, planetary perturbations can alter the orbit of a comet. We can see here the orbit of Comet Wild 2, which in September 1974 passed within 900,000 kilometres of Jupiter, and you can see how its orbit was made dramatically smaller and its perihelion distance decreased.
It's generally Jupiter that's the culprit. I think of Lexell's comet of 1770, which was a naked eye object, and then it had a close encounter with Jupiter, and it's never been seen again.
And it's also interesting that Jupiter tends to collect comets as well. If we draw the orbits of a number of short-period comets, project them onto the plane of Jupiter's orbit, you can see here a number of them. Their aphelion distances, their greatest distances from the Sun, tend to cluster around Jupiter's orbit. So Jupiter is tending to gather in comets into the Jupiter family, as it's called.
And with these comets, we can actually see them wasting away. Think of Encke's comet, period just over 3 years, the shortest known, being seen at many returns, and apparently in the last century it was quite prominent. This is a drawing made in 1870, and there we see a head and quite an appreciable tail. But Encke's comet is not nearly so bright as that now.
No, of course, in Encke's comet, which has the shortest period known of only 3.3 years, the ageing processes are greatly accelerated, and it's losing a fraction of 1% of its mass every time it goes round. There are various estimates for how long it will last, but the most pessimistic make that perhaps in 150 years, Encke's comet will no longer be with us.
I'm sorry about that. It's an old friend. But you know, the inner part of the solar system is a very dangerous place for comets. So much can happen. They may waste away. They may hit the Sun, as Howard Kuhlman-Michaels did, and actually photographed by a satellite in the act of being destroyed. And then a comet may actually be perturbed by a giant planet, generally Jupiter, and thrown out of the solar system altogether. And that happened with Comet Arend-Roland of 1957, the subject of our very first Sky at Night program. That will never come back. And of course, there's activity also in cometary nuclei. They may flare, or they may very often fade.
Yes, the surface activity of a comet's nucleus is very complex. The surface is covered with a dark dust crust or mantle, and where there are cracks and fissures in this crust, the underlying dirty ice is exposed to the Sun's radiation and heat, and the ice sublimates, forming the gas and dust jets which spurt out. And occasionally the force of these jets breaks off sections of the mantle, and the comet flares dramatically in brightness. One example of this was Comet Tuttle-Giacobini-Creysack. You can see here that faint trail of the comet. But in May and July of 1973, it brightened by 10,000 times, so there was a tremendous outburst there. And of course, the opposite can also occur. Sometimes a comet will be missed for several returns, and it will fade, or it may even break into a number of fragments.
Well, I suppose the most famous case of that is Biela's comet. 1845, it split in two. And the twins came back again in 1852, and they certainly don't exist. They've never been seen again. They've broken up.
No, I mean, Biela's comet had a period of 6 3/4 years, so it was one of these short-period comets. And after it broke into two, as you say, it was seen again in 1852. The two components were further apart, and it was never seen again, although there were two spectacular displays of shooting stars or meteors in 1872 and 1885 connected with the disruption of the comet. And more recently, the Great Comet West of 1976, that beautiful comet.
It was a lovely one.
It was indeed. The nucleus of that was seen to split into 5 fragments in March of that year.
There are at least 8 periodical comets seen in the last century, which used to return regularly and have now been lost, probably because they've disintegrated. On the other hand, it may be that we lose some comets simply because we don't know their orbits sufficiently well. And one of those could be Swift-Tuttle, seen for the only time in 1862 when it was quite bright. And Swift-Tuttle is of special interest because it's the parent comet of the Perseid meteor stream. And next month is Perseid time.
Yes, I mean, the Perseid shower is the most reliable of the annual meteor showers. This year it peaks on the early morning of August the 12th. And as you say, it is connected with the dust and the material ejected by Comet Swift-Tuttle. You can see those drawings there of the dust, the fans ejected at the 1862 return. And this year, it'll be particularly interesting to watch the Perseids, although there will be interference from moonlight. Yeah. Last year, Japanese observers recorded an intense burst of activity, and it'll be interesting to see if that happens again.
I wonder. Now, but what about Comet Swift-Tuttle?
Well, of course, we only have seen it once for certain, the return of 1862. And if you can see here, in 1862, the comet passed perihelion on August the 23rd, and the Earth and the comet were fairly close to each other. So it was a spectacular object, it was visible to the naked eye, and at the end of August, it had a very respectable tail. And the head of the comet was bright, there were fans and jets of dust, as you can see here. So the actual comet itself was a spectacular object. But of course, whether it will return again is another very interesting point. It was assigned a period of 120 years based on observations in 1862, so it was expected back between 1981 and 83, but it wasn't seen.
Can it have come and gone unseen?
Well, that is possible. If we look at the orbit of Comet Swift-Tuttle, we see that, of course, it's got an orbit of around about 120 years, so it's quite a large orbit. It goes out way beyond the furthest planets, spends most of its time below the plane of the planets, and there is its orbit shown on that diagram with the other planets to scale. And this model here shows the inner part of the orbit of Swift-Tuttle. There's the orbit of Swift-Tuttle coming over there. This is the orbit of Jupiter. That's the orbit of the Earth with the Sun in the middle. Now, when the comet reaches perihelion, closest point to the Sun, about there, it passes down through the descending node where it crosses the Earth's orbit a bit later. Now, if a comet reaches the descending node in August or September, the Earth is fairly close to it, we get a good view of it, the comet will be a bright naked eye object. But if the comet passes perihelion in January or February, the Earth and the comet will be on the opposite sides of the Sun, and we may well miss it completely.
Well, you know, we could have got the period wrong, because after all, there are suggestions that the comet is identical with Kegler's comet of 1737. And if that is true, then the period could be nearer 130 years than 120.
If the period was 120 years, we'd have expected it to have returned between 1745 and 1750. But there was no comet like Swift-Tuttle seen at that time. But there was a comet seen in 1737 by Kegler, a Jesuit missionary in China, and this looks very much like Swift-Tuttle. And if Comet Kegler and Comet Swift-Tuttle are one and the same, its period may be nearer 130 years rather than 120 years, so it could be back later this year.
Well, if it does come back, where do you think we're going to find it?
Well, it all depends when it comes to perihelion. If it comes to perihelion in November, then, of course, we will get a moderate view of it. You can see here on this chart, it passes from the northeast through north over to the northwest and passes through the bowl of the Plough in mid-September. And it will be a reasonable object, probably visible in binoculars. But if it comes back 2 months early, in August or September, it'll be much brighter, visible higher in the sky, and could well be a reasonable object. But if it comes back 2 months later, in January of 1993, it'll be lower in the sky, its motion across the sky will be less, and we may well not see it at all.
Well, what's your bet?
My bet is that if it was coming back in August or September, it would have been found already. And the fact that it hasn't, I think, means that if it's coming back at all, it'll be towards the end of the year or beginning of next year, so we may not see it.
Meanwhile, you and I are going to have an energetic hunt for it, John, and let's
Indeed
hope we succeed. But the story of Giotto may not be over even yet. There's a chance that in a few years it may be possible to send it on to yet a third comet. And if so, Susan, do you think your experiment is still going to go on working?
Our experiment has worked beautifully for the last 7 years. In 1985-86 it worked on the way to and at Comet Halley. In 1990 it worked during the historic Earth flyby because, you know, Giotto was the first working spacecraft that we encountered the Earth from deep space. And then it worked in 1992 at Grigg Sjkellerup. So would it work if it was called upon again? Why not?
I'm sure it will. Many congratulations. Let's hope that Giotto does go on to another comet and that our experiment continues to work. Susan, thank you very much indeed. And meanwhile, let's hope that sometime within the next few months we can report the discovery or rediscovery of Swift-Tuttle. I very much hope so. Also, don't forget our phone line. If you want the latest information about astronomy, then dial 0898 666 000 and we'll tell you what's going on. Next month, we have a very interesting program about who really invented the telescope. Until then, good night.